Welcome back, guys. I think I'm catching a cold. This is part 3 of a 3-part series on the Reliance Controls ProTran2 manual transfer switch. In the last video, we covered the basic install of the MTS, which includes the standard circuit wiring, load balancing, and bonding. In this video, we will cover shared neutrals and AFCI/GFCI circuit breaker wiring. So what is a shared neutral? It is a wiring method that uses a single cable with 2 hot wires, a common or shared neutral wire, and a ground wire. This is known as multi-wire branch circuit. So these can be problematic in a multitude of ways, mostly being that if you do not wire it correctly, the neutral can become overloaded, get hot, and even catch fire. Secondly, there is between 2 legs, the black and the red, there is a 240 volts. So this makes it a potential hazard when working with these circuits. So in my house, I have 4 shared neutral circuits, or pairs. 2 of those pairs are located here in the kitchen. One pair is the refrigerator, and these 2 outlets on the back labeled 3C. The other pair is the microwave, and these outlets on this back wall here labeled 2B. So for the microwave pair, the black wires connect to the outlets on the back wall here, and the red wire connects to the outlet for the microwave up there. Likewise, for the refrigerator pair, the black wires connect to the outlets on the wall, and the red wire connects to the refrigerator. So for the microwave, I have the outlet on the MTS on circuit 1A, and the outlets on the wall are 2B. So they're located on separate phases on the MTS. They're next to each other, but they're on separate phases. Likewise, for the fridge and the outlets back here, these outlets are labeled 3C, and the fridge is on 4D. Let's go see how these are wired at the main service panel. Now, if you were going to work on the microwave pair, looking at these circuit breakers, you would not know that you would have to turn off both sides of the circuit to make it safe. Remember when I said the black and the red wire are on opposite phases? And between them you're going to have 240 volts. So it's not really obvious. I am not an electrician. If you guys do not understand this inside and out, backwards and forwards, call an electrician. Shut off our main power. That will always be hot. No voltage, no voltage, no voltage. We're good to work on this panel. Alright, I'll try to explain this as clear as possible. So for me, I have these 4 pairs, like I mentioned. I labeled them 1, 2, 3, 4. So the big red flag for me was I have these tandem breakers, right? There's 2 circuits on each physical breaker, and each of these physical breakers are located on separate phases. So this is on phase 1, phase 2, phase 1, phase 2, phase 1. If you look at each pair, this is a single, so this is not included here in this example. So if you notice, there's a pattern here. The red wire is connected to the bottom position on this top physical breaker, and the black wire in the pair is separated, is connected to this second physical breaker on the top position. And that goes down the line. So 1, 2, 1, 2, 1, 2. This is my transfer switch. I already did one of these sides. The main clue here is that you'll have one of the wires on one physical circuit breaker located on one of the phases, and the other wire will be connected to the other circuit breaker on the other phase. The other clue for me was they actually labeled these as pairs. So this one reads refrigerator and kitchen GFCI, and if you trace this up, it'll probably be a 20 amp or yellow Romex, and it's going to have the red, black, ground, and neutral. So that neutral right here is the shared neutral for this pair, and I marked it. Alright, so my other clue, these are 120 volt breakers because they only contact one side of the bus, this side or this side. So if you have 120 volt circuits and they're split like this, you know for a fact that's going to be a shared neutral. I'm not even sure if this method is acceptable these days, because you would have to turn off both breakers. Or the safer example would be to have a double pole common trip breaker, and you have your side 1 and side 2 go into your two 120 volt circuits. So at least if you turn off that breaker, it's going to shut down both of those circuits. The other side of that double pole breaker I just showed you is especially dangerous. Here's why. And that's because it's wired to this receptacle. This receptacle powers two 120 volt circuits individually. The top one goes to the dishwasher, and the bottom one goes to the garbage disposal. Now the garbage disposal is on the switch, so at least one side is switched. Both the black and red wire terminate in the same receptacle box. If we take the box out, I can show you on the outlet that the tab is broken. We have two individual circuits in the same box. Okay, so you can see here we have an actual 20 amp rated outlet, and on one side we have the common neutral, and you can see the tab is in place right here. Now this is where things get interesting. On the other side we have the black and we have the red, but the center tab is broke, so these are not connected. Each side of the circuit power one receptacle. So if I probe the black and the red, you can see on the meter we have 245 volts. All it takes is you touching from there to there, and you're going to get shocked. 240 volts. So that's probably the reason they put that circuit on a double pole common trip breaker. As for the tandems, they probably have junction boxes in the ceiling where the homeowner cannot access. So that's why they decided to use tandems, even though I hate the fact that they use tandems. So luckily for us, we can have the opportunity on the MTS to change these breakers to a common trip double pole breaker. So here on the MTS we have those two shared neutral circuits. We have the first one and second one. This first one is the microwave circuit, okay, and that's paired with the kitchen GFCI. That's on this double pole breaker here. So if any one side of that circuit trips, it's going to shut down both circuits. Likewise, if we need to work on that circuit, we just turn off this breaker and both sides of the circuit are shut down. Alright, so here is the common neutral for the microwave circuit. I've marked it so we can do a test, and we'll see exactly how the current behaves on a shared neutral. Alright, so I have the power back on, and we are going to test the microwave circuit. We're going to run these circuits individually, and then we're going to run them at the same time, and we're going to watch the current on the meter and see how it behaves. Okay, so for this test we're going to use the toaster oven, plug it into the 2B circuit, and we're going to use the microwave plugged in to the other side of the 2B circuit, that is 1A. We'll put this on 2 minutes and we'll go check the current. Okay, you can see we are getting 14.3 amps from the microwave. Okay, microwave is off. Now we're going to test the other side of the circuit. Let's turn this sucker on high and let's go. And again, very similar, 14.56 amps. Okay, so for this next test, things are going to get a little bit weird. So we're going to run both appliances at the same time. So you might think we're going to get 14 plus 14, right? That's 28 roughly. Watch this. Start and start. And look at that, it's just 4.6 amps. That's right, 4.6. Now what the heck's going on? Now I'm going to run both appliances and switch off one side of the circuit while they are running, and we'll observe the current. Go and go. Okay, we have 4.6 amps. Now I'm going to switch off 1A, which is the microwave. And look at that, jumped right up to 14.4. So what the heck is happening here? This is a little bit on the edge of my knowledge, but I'll link a video which is a good description about what's going on here in the description below. So what happens is the neutral ends up carrying the difference between the two loads. So the key here is we have two 120 volt circuits that we're dealing with, and if they were both running at the same time, you would think that the current would be doubled, but no, it's going to be the difference. And if they were on the same phase, God forbid, you would have 28 amps on a 20 amp rated wire. That would be very bad. Now this is only a problem if you are moving both sides of the circuit to the MTS. In other words, you're moving the full pair to the MTS. So my house has 4 pairs. 2 of the pairs I'm moving both sides over. The other 2 pairs where I'm just moving a single side over, I don't have to worry about this because it's just one side of the circuit. So on the MTS we have the microwave and kitchen GFCI pair. That's circuit 1 and 2, 1A and 2B. Those are on different phases because these circuits are on phase 1 and these circuits are on phase 2. Likewise, the kitchen sink GFCI and the refrigerator, those are located on 3C and 4D. So 3 and 4 are located on different sides of the MTS. So a good way to think about it, if you keep the pairs together and you move them to the MTS, so they're right next to each other, 1 and 2, they're going to naturally land on separate sides of the bus. So this position is 1, this is 2. 1, 2, 1, 2, 1, 2, and so on. So keep your pairs together, but on separate phases. So a little Easter egg here. The second pair, the refrigerator pair, I've done something a little bit different. So if you compare the labels from the main service panel and the labels on the MTS chart right here, see if you can find out what I did. It's a tip. It's for load balancing reasons. Alright, so we're going to do the 1A circuit and the 2B circuit. So these are shared neutral. One side is on this breaker and one side is on this breaker here. Because we have reds in our circuit breakers on the shared neutrals, we're going to be putting the black to the red and the red to the circuit breaker. I'm going to take out the red wire. Gotta open up the circuit breaker all the way because this 10 gauge wire is probably about as large as you can fit inside one of these breakers. 20 amp breaker. Tighten it down. Okay. Oh, man. Our black to our red. This is where things change up from a standard circuit. So this is the exception. That completes 1A, which is our microwave side of the shared circuit. Now we just got to do 2B, that's the kitchen GFCI. Okay, gonna remove the black wire from the circuit breaker. Okay, we can stab our B input wire from the MTS into our circuit breaker. And this time we're going black to black. So once you're done, you should have all reds on your breakers, except for this one and this one, which I didn't end up moving to the MTS because there's no label there. Alright, so that leaves us with the AFCI breakers right here. So let's go test these circuits that we just wired up, and then we'll do the AFCI circuits. So on the MTS, all the circuits are in line mode except for the microwave and kitchen GFCI circuit, which is on position 1 and 2. So we're going to turn on this double pole circuit. So looking at the inverters, only about 100 watts coming off this one, and there's nothing coming off this one. So if my calculations are correct, you're going to see some serious shit. So remember the test we did when we had the microwave and this toaster oven powered from the grid? We saw only about 5 amps on the neutral. So now we're not going to look at the neutral, but we're going to be able to see the power from both devices, but separate on each inverter. Remember, this is wired to the secondary inverter, and this is wired to the primary inverter. Turn this one on. I can hear him humming already. All right, the primary inverter, L1, is pushing 1.71 kilowatts, and our slave inverter, L2, is pushing 1.78 kilowatts. Cooking with solar, baby. Dinner is served. So what are AFCI circuit breakers? AFCI stands for Arc Fault Circuit Interrupter. It's a special kind of circuit breaker which monitors the neutral for things like loose or arcing connections. So this particular one is the pigtail version. Now you will find these with the pigtail. This is this wire here. It's like a pigtail. Or you will find them with the plug-on neutral. They'll have an extra pin on the bottom which plugs onto the neutral rail if your panel supports it. Now the MTS only supports pigtails, so you cannot use the plug-on neutral variant. In fact, they sent me the wrong ones and I had to send those back to finally get these. So because the way Reliance wants these to be wired, if your main service panel, if you have a newer house, they may have the plug-on style. If you have the plug-on style, you cannot access this wire. So you'll have to swap all those plug-ons for the pigtail version, and these are not cheap. These are like 40 to 60 bucks each. So if you have a panel that's full of plug-on style arc fault breakers, that's going to get quite expensive. So for the sake of the video, I am going to refer to the pigtail as the neutral reference or neutral input wire. So per Reliance, they want the neutrals to be wired in series. I actually called them on this and to see if this was in fact true, because this schematic for some reason is excluded from some of the documentation, so you'll find online. So some documents will have this particular page and some will not. Let's familiarize ourselves with the arc fault breaker. So here's our pigtail or neutral reference. That's the input. And then on the breaker itself, you got two outputs. You have the neutral output, which is pointing to this pin here, and you have the load output here. So your neutral wire going to your load is going to be here, and your hot wire going to the load will be here. So let's go over how Reliance wants us to wire these. So if this breaker, let's pretend this breaker is the one in your main service panel, and this one is the breaker in your MTS. So the neutral output on the one on the MTS is going to go through the wire, the additional wire, neutral wire that we had to install in the harness. Is going to go to the input of the breaker in the main service panel, and that's where we get our series connection. Let's take a closer look at the schematic. So this block here represents the arc fault breaker. This part right here, that's the neutral input or the pigtail. This wire here is the load neutral output, and this is the load power output. So what they want you to do, starting from the main service panel, this is the neutral, the big neutral that comes with the MTS, that connects to the main service panel, goes to the MTS, right? And then from there, it goes, you're going to have to tap this, and it's going to go into the pigtail neutral input on the circuit breaker. Then the output, neutral output, goes out into the neutral input on the AFCI in the main service panel. And then it continues on to the load neutral output to the load. So the load side is wired exactly the same as the standard circuit breakers. The only difference is we're going to have to tap into the neutral, combine the pigtails, and then we're going to connect our additional wire to the other circuit breaker. And for our multi-tap here inside the MTS, we're going to be using a 4-slot multi-tap Polaris connector. Clear as mud, right? I hope I explained it good. So this brings up a couple of questions I had. Let's just spitball here for a minute. If let's pretend that this is the MTS breaker, right, and this is the one in the main service panel. My thought was, before I found this circuit, was, oh yeah, maybe you just connect both these outputs together, right, along with the load output, and then do it that way. But Reliance says that the circuit breaker will not be able to properly read the neutral line. Which brings up another question. On this circuit breaker, when it trips, does it actually interrupt or break the neutral path? Or does the neutral simply get scrutinized or listened to, in order to trip the breaker, and then when it trips, it only trips the hot side? So I guess we'll find out, because if this is in series, right, the neutral is passing through both breakers in series. If your MTS is in line mode, and then you were to flip the breaker in the MTS to the off position, would it actually stop current flowing to that circuit, or would it keep working? So this is something we're going to find out. These are the bedrooms. This is the 7 is the master bedroom AFCI, and the 8 is the front bedroom AFCI. I'm just going to probe both sides of the bus here. Should get no voltage, no voltage. We're good to work on the MTS. All right, so the first step is we got to swap our regular circuit breakers with the AFCI version. So I already got this one removed. We'll just pop in the new one. It's that easy. Just pops right on there. So now we'll just put our load side in. Okay, so the next step is connecting our load neutrals. Now these are the 2 wires that I added to the harness in the install video. So these go to the main service panel, and they'll connect to the pigtails on the AFCI breakers that are already in the main service panel. So this is number 7, that's going to go here, and this is number 8, going to go there. I really like these breakers because it tells you, hey, the neutral is on the left. Can't screw it up. What would be nice actually is to get that wire underneath this wire stay right here. I need to get this pigtail out of the way. Circuit number 8. All right, the circuit breakers are wired. Okay, all we have left to wire is the pigtails. So the standard installation, you're going to run the main neutral, right? That comes from the main service panel, and it goes right to your generator inlet port. Well, what we have to do is tap into this neutral. So we're going to use this multi-tap. We're going to splice this neutral here, and then we're going to tie everything together. So first we're going to remove the neutral from the generator inlet port. Alright, so we're going to put the neutral in there, coming from the main service panel, just to show you how deep that went. We're only hitting copper. Make sure it's nice and secure. Okay, so now we need to restore the connection to our generator inlet port. So we're going to jump from there over to our gen inlet port neutral. So the multi-tap, you're going to have to probably put it over here, because when you try to put this generator inlet port, this port takes up all this space right here, and it's just going to be too cramped in there to try to put this over there. So keep that in mind. Okay, now we can complete the neutral connection to the gen inlet port. Alright, so the final step is to connect our pigtails and splice them into our neutral. Okay, that's number one. Okay, we are done. Alright, so there seems to be a problem with this multi-tap. It keeps on breaking these wires. So either the screws are too aggressive, or I gotta get a different multi-tap. I really wish these were stranded. It would work a lot better with stranded wires. NSI, easy splice. Very nice. A relatively flat bottom. Should work nicely. And then you enclose the splice in this gel encapsulated container. That helps to seal it up. So it does require a fair amount of clamping force to close it. So don't close it until you are ready, because it's not easy to open back up. Okay, I got one neutral already connected. Connect up the other one. Okay, now our main neutral is spliced in. I got that one sitting in there. Good. This is actually for outdoor weatherproofing. I could probably just tape this up and be good, but what the hell. So put on the goopy box. No. Get her nice and lined up. I can see where people complain about these not closing because of the sides. Alright, so I cut out the side for the big wires with my snips. That should be good enough. This is crazy. I have to use some vice grips. Actually, that works quite well. Gotta squeeze that goo right outside the corners on the two sides so that it makes that seal. That's crazy. Don't want that thing to pop open. Done, finally. Let's button it back up. Okay, everything's back together. We can test our AFCI breakers. There you go, LED. There you go, LED. Self-test complete. Now we can do a manual test. Awesome. So Reliance actually makes a neutral kit for these transfer switches. It's called the NK8 or the NK10. The kit includes an isolated neutral bar, which is the smallest form factor device you can use inside the box. And it will also isolate the neutrals from the chassis, because you do not want to create a ground neutral bond inside the MTS. It also comes with gray, a set of gray neutral wires. They're not white, they're gray. And I think it comes with conduit as well. I'm not sure, but check it out. It's NK8, NK10. I'll put a link in the description below. And yeah, I wish I knew about that, but for me, I only had 2 circuits, so it's not a big deal. But if you got a lot of neutrals to do, definitely look into getting that neutral kit. And special thanks to my viewer, Michael, for sending that email to me. It's really great when the community chimes in, and so we can all learn and add more value to the video. So thanks a lot, I appreciate it. And Reliance actually has a good tech support team, so you can email them, you can call them up, they'll answer your questions. I am not an electrician. Working inside a main service panel is dangerous. If you do not understand this inside and out, backward and forward, call an electrician. Okay, so here are our 2 AFCI circuits, 7G and 8H. And here are the 2 neutrals for those circuits that we added to the harness during the install video. Here's the 2 input wires to the MTS, and here's the 2 output wires from the MTS. Okay, so each AFCI circuit will have 3 wires. So the first thing we got to do is remove the pigtail from the neutral rail. pop it out. There we go. There's our pigtail. Make sure we put that screw back. See, they used stranded wire on this. I love that they used stranded wire. Okay, so the pigtail is going to connect to the neutral that we added to the MTS harness. And then the load neutral is going to stay where it's at. And then just like the regular circuits, it's the same from there on out. We pop out the load, put our red wire in, connect our black wire to the load wire. So we're going to connect these two together. Sorry for the mess, guys. It's just so many wires to deal with. But finally, we get to connect stranded to stranded. So that's a nice change. Pop out the load wire. Put the red wire going to the MTS, the input wire, into the where the load wire was. Alright, so I got the circuit breaker back. I always like to give a good tug on the back of the circuit breaker to make sure it's actually landed inside of the grooves here on the rail so that you know it's seated. So we're good. Okay, now we just connect the black output wire from the MTS to the load wire. Alright, so we're currently running everything off of solar power. We're in gen mode. I have the main utility main breaker off. Now watch what happens when I turn on the main breaker, and watch what happens to the AFCI breakers. They trip. We'll just leave those off. So one of my viewers actually sent me an email from Reliance regarding this issue, and this is perfectly normal. What happens is the AFCI breaker, when there is a change on the bus, it detects the difference between the utility power and the generator power and trips the breaker. You can see here on the MTS side, the breakers did not trip. If we switch from gen to line mode for those circuits, they do not care, because these breakers only ever see power from the gen side. So now that we switch those circuits to line mode, we should be able to turn these breakers back on. Time for the Super WAZOO test. I have all 10 circuits wired up to the house. Let's see how much power we can push through the MTS. The MTS is supplied by this 40 amp breaker. That's 120 volts times 40 times 2 for a total of 9600 watts. We're going to watch the shunt and see how many watts we're pushing through the battery. This will also tell us how well balanced the system is through the MTS. We're going to go through and turn on all the lights first, and then we'll turn on the heavy loads. So right now we're just pulling 60 watts. Let's begin. Outside lights, router, telecom gear, bedroom TV, mini fridge, bathroom lights and fan, living light, more lights, the other TV, and the closet light. Okay, we're back, and we have a baseline with all the lights and fans on, and the TVs with the regular appliances like the refrigerator and the chest freezer and the water cooler, and we're pushing 1200 watts. Inverter 1 is pushing about 600 watts. Inverter 2 is pushing 530 watts. So we're looking pretty good balance-wise. Likewise, on the MTS, you can see the meters are just about at the same position. So we're balanced. Let's go jack it up, turn on the big stuff. All right, we'll start with the dryer. Gaming PC, running a game. I'm getting nervous. Microwave, air fryer, rice, toaster oven. Oh boy. Boy, the inverters are singing. 4.17 kilowatts on one inverter. 2.5 on the other inverter. Just about 8,000 watts. 7,800. We need more. Look at the MTS. Meters are about halfway on each meter. No sweat so far, right? 2.5. Almost 5. This inverter can max out at 6,000 watts as the max for that unit. Let's turn on this heater. $8,300 watts. 8,300 watts on the shunt. So about 4,000 on that inverter. 5.2 on that one. 10,000 watts. This breaker might trip. This is the hardest I've ever pushed it. I think we could stop. Wow, that was a lot of power. It's always good to do a stress test. It's funny because if I preload the inverter with about 3,000 watts, it still has 3,000 watts of overhead left over, and I turn on the dryer and the grid assist is connected up to the inverter would rather prefer to kick to the grid to handle that surge. So that's why I remove the grid input so the inverter has to dig down deep to power the loads. But it can do it. If I start with the dryer and then add the other loads on top and the inductive loads, then it slowly builds up and it can handle the load. Just in time too, because it looks like a huge storm's brewing. Good thing this video wasn't about how to make a nice looking panel, because those wires got pretty messy in there. But hey, gives me an excuse to go back in there and fix those tandem breakers, and while I'm at it, I'll fix up the wires. To recap on a couple things about shared neutrals, just remember if the black and red wire terminate in the same box, you're most likely dealing with a shared neutral, so be careful. Also, if you see a red wire wired to a 120 volt receptacle, you may be dealing with a shared neutral circuit. If you need more information on shared neutrals and how to make them safe, please see the reference video in the description below. So in my experience, I cannot recommend the Polaris multitap for small gauge wire, number 12 or number 14. It's fine with larger gauge wire. Instead, I would recommend using an isolating neutral bar or the NK8 or NK10 neutral kit from Reliance. So something I noticed with the Siemens AFCI circuit breaker, I have a mini fridge in that one bedroom and it's been causing nuisance tripping about once every week. So I might have to switch that breaker for a different brand. So that's something to consider if you're going to be putting it on a circuit that has a compressor load like a water cooler or a mini fridge of sorts. Remember when we talked about the AFCI breaker, the neutrals, how they're in series? Well, it turns out that the neutral is just listened to. It is not actually broken when the breaker is tripped. So if your MTS is in line mode and you turn off the AFCI breaker, it will not interrupt the neutral circuit going into the main service panel. So the circuit will continue to work. Well, I hope you enjoyed this series on the Reliance Controls ProTran2 manual transfer switch. I certainly learned a lot. If you don't want to wait for my next video, check out this one right here. And as always, thanks for watching. Guess I won't be needing these any longer.